So this question asks, what is the angle of inclination of the cone formed by this shaded region? So first of all, we want to take this shaded region, which is half a circle, and when we fold it back on itself, it's going to make a cone. And what we're looking for is the angle of inclination, so this angle in here, which we'll call theta. Okay. Now that angle is going to be made in this right triangle. So what the goal is then, we need to figure out the lengths of the sides of this right triangle. So this red one that I've highlighted here. So we're going to start by, we haven't been given any measurements, so you could do this by arbitrarily giving, the radius a length, but we're just going to start with giving the radius a length of r. So we're just going to generalize it for that big R. And the half circumference here that we get from that big R in green is going to make the full circumference of the cone, the bottom circle on the cone. And if that radius of the big circle is big R, that gives us the slant height along the red triangle as the same. That represents the same as the radius of that big circle which we formed the cone out of. So we just need one more length in that red triangle in terms of the radius. So what we're going to do then is, first thing is, I'm going to write an expression for the half circumference. So we know that the full circumference of that circle is going to be 2 pi times r. So I want the half circumference. So this gives us a half circumference of pi r. So that's going to be pi r halfway around like this. That makes a full circumference of this circle. So I'm just going to draw it over here. We have our full circumference here. That's going to be, this is going to be pi r is going to be distance all the way around. Okay. And we want to find the circumference of the smaller circle. I'm just going to label that as C for now. And that distance there, C, is going to be the full circumference, pi r. And since it's going to be 2 pi times C, I'm going to divide both sides by 2 pi. And then that just leaves me with C. So the C value is, and maybe I should change that to a different variable here. I'm going to maybe change that to little r. We'll call that little r. That little r value is going to be equal to, the pi's cancel out, it's going to be exactly half the length of the big radius. Okay, so the diagonal length in the red triangle is r. The length is going to be half of r is going to be the horizontal length of that red triangle. So I'm just going to redraw that red triangle. This is a triangle that we're going to work with to get the angle theta. So that's our angle theta that we're looking for in here. This is half r, and this is r. So I have two sides of a right triangle, so I'm going to write it this way. Cosine of theta, so I have the adjacent and the hypotenuse. So r over 2 over big R. Simplifying that ratio, basically the adjacent is half the length of the hypotenuse. So I'm going to end up with the r's canceling out, and I get cosine theta is equal to 1/2. So we can solve for that angle by using the inverse cosine, and that angle works out to be exactly 60 degrees. So we wanted, first of all, write an expression for the half circumference of the big circle in terms of that big R. We want to come up with the radius of the small circle in terms of that same big R, and then that allows us to get a ratio which we can apply inverse trig to find the actual angle of inclination in that problem.